I am Dr. Rajiv Mishra from IIT Patna. The topic of this lecture is global state and snapshot recording algorithms. So, content of this lecture will discuss about the global states. There are two types of global state, consistent and inconsistent global states, and we will also see the model of communication and the snapshot algorithm, specifically Chandy-Lamport's algorithm to record the global snapshot. So, what is a snapshot? So, you can see in the picture that all the people they collect at one place and a photographer take a snapshot. So, this is called a snapshot, but if what if the people do not collect at one place and still you want to take the snapshot, it is called a distributed snapshot. So, how do you calculate that global snapshot in this distributed environment? So, take this environment, the distributed system where these particular processes are running at different places around the globe, and you want to take a global snapshot in this environment, that is called a distributed snapshot. So, that is not so easy. So, we are going to see this kind of topic. So, the use case will be, for example, if you are having the IoT devices which are deployed in a particular city, so many number of devices, and often they are connected with the edge and then it is connected through the cloud. So, if you want to monitor or debug a particular instance or the events, then you sometimes require the global snapshot if they are also having the actuators. So, this kind of use case in IoT, that is applying global snapshot, distributed snapshot, is also one of the most important distributed system problem which is applicable in the IoT system. So, let us see, as far as this edge data center and cloud data center and IoT devices, this all becomes a distributed system and how we are going to take a global snapshot. So, in the cloud, each application or service is running on the multiple servers that we have seen in the previous lectures. So, the servers handling the concurrent events and often interacting with each other, this is another part of the model. So, the ability to obtain the global snapshot of this kind of distributed system is sometimes important for the applications such as the checkpointing, that is you can restart the distributed system on the failure. That means, if let us say some device is failed, so how do you restart that application which is enabled with the help of IoT devices. Similarly, the garbage collection of the objects. So, objects at the server that do not have any objects within pointer to that. So, sometimes that is also garbage collection requires a global snapshot recording for that. Sometimes the deadlock detection, which is useful in a database transaction systems, and termination of the computation, that also requires the global snapshot. So, global snapshot algorithm is the basis of many applications which is running in this kind of environment which is called a distributed system. So, how do you record the global state in this environment which is called a distributed system on the fly without stopping the current application which is running? So, that is most important part. So, lack of global, why there is a problem, what are the issues which this particular algorithm will need as a model. So, in a distributed system there is a lack of globally shared memory, we do not expect a common or a shared memory. Also there is a global, there is no common clock and all the devices are running autonomously with their own clock. Similarly, the messages which are being exchanged, their delays are also unpredictable. So, this makes this distributed system a problem of global snapshot recording and non-trivial. So, it is not like the people gather at one place and the photographer takes a snapshot, it is quite non-trivial. So, this lecture first defines some few preliminaries such as consistent global states, and then how these particular, what is the computation to be done to do this compute consistent in a distributed snapshot recording. Then we will use an algorithm that is given by the Chandy-Lamport algorithm to determine on the fly snapshot recording in this way. So, let us understand the system model in which this algorithm will be explained. So, the system consists of n different processes that are connected by the channel. So, here the use case may be that you have n IoT devices and these IoT devices are now connected in a form of a mesh network, and this particular model is fitting into that also. So, now we have also assumed that there is no global shared memory out of these n systems, and also the physical clocks and process can communicate only by the messages through the communication channel. So, if a process Pi and Pj, if they want to be connected or if they want to communicate using the messages, then we assume a communication channel between process Pi to Pj and we state it as the state of the channel. Sc means state of the channel between I and j. So, the actions performed by these process are modeled as three different types. So, internal events means all the events which are happening inside this particular process called internal events, and whenever this particular process will send a message called message send event, and when the process is received, then it is a received of a event. So, all the events are divided into three types. One is called internal event, which is happening in these inside these particular processes, or when a process will send a message, this will be the second event. A third event when a process will receive the message. So, there are three different events to make the system model usable for this particular algorithm. So, for a message Mij that is being sent between the process I and process j called Mij, that is the message Mij which will be sent by a process Pi, send of Mij, denoted by send Mij, and similarly when process j will receive this Mij, it is called the receive of this particular message, and these send and receive events will be denoting this message flow. So, the system model another assumption is that at any instant the state of a process Pi will be designated by local state of I. So, Ls of I means the local state at the process I is the result of the sequence of all the event executed by Pi by the process I up to that particular time instant. So, for an event E and a process state LSI, E is a part of this local state LSI if and only if E belongs to the sequence of events that have taken place inside process I to that particular to the local state. Similarly, for the event E and the process state LSI, if E is not there into the local state of I, that means if and only if it does not belong to the sequence of events that have taken process Pi to the state LSI. Similarly, for the channel between I and j, the following set of messages can be defined based on the local state of a process I and j. So, the message is said to be in the transit, that is between local state of I and local state of j, there is a message which is there. So, where send of a message Mij is available in the local state of I and it is not received in the local state of j, then this particular message which is sent which is not received is said to be in the transit. Now, let us see that after defining the processes and the local states, let us see that what do you mean by the consistent global state. So, the global state of a distributed system is a collection of such local states of the processes and the channels. So, notably the global state GS is a union of all the local states of different processes and the union of all the channel states called state of a channel between I and j. So, the local states and the channel states together is called the global state. So, global state GS is said to be a consistent global state if and only if satisfies two conditions. So, condition 1 says that if there is a send of event, send of a message Mij is available in some of the local state of a I, this implies that Mij is there either if it is there in a state of a channel, that is the message is either flowing in the channel or it is received in the local state if it is sent by a particular process. So, if a message is sent, then it must be either in the channel or it is received at the receiver end. The second condition says that if the message Mij is not in any of the local states, so this means that neither it will be appearing in the channel states nor it is there in the receive of that event Mij. So, if these two conditions C1 and C2 are satisfied in that global state, then that global state is called a consistent global state. So, a distributed system execution, let us trace back. The global state is consist of the local state ls1 and so on is inconsistent because P2 has recorded the receipt of a message M12, however, the state P1 has not recorded its state as send. Let us see here in this example. This global state is called inconsistent. Let us see where is that ls1 of 1, then for 2 3 and then 3 3 and then 2 4. So, this particular state you see that if you see over here that the message is received, but its send is not recorded, therefore, it is called inconsistent global state. So, this is the send of a message is not there, but receive of a message, receive of M12 is there in the local state or in a global state of 1. This is the first global state. Now, let us see the second example. The second example says that GS2 is consistent. Let us trace what is GS2. So, local state of 1 2 this, then 2 4, then 3 4 and then 4 2. So, this is called consistent. Why? Because you can see that this send of an event is already there because receive is there into the. So, all the messages either they are who are there in the send, they are either be received or is in transit, therefore, it is called consistent state. Now, let us see the third one, which is called the strongly consistent. Strongly consistent GS3 stands for 1 2, then 2 3, then 3 4 and then 2 4. So, this particular snapshot, this is GS3, here you can see that there is no message in transit, all messages which are sent they have been received. So, this kind of global state is called a strongly consistent global state. So, recording the global state of a distributed system without stopping is a very important paradigm and is often interested in the analyzing, monitoring, testing and verifying the properties of distributed applications or the systems and through the algorithm. So, design of efficient method for recording the global state of a distributed system becomes very important. Now, let us see what are the issues are there in recording the global state autonomously with the help of algorithms. So, there are two issues need to be addressed. One is called issue number 1, says that how to distinguish between the messages to be recorded in the snapshot from those not to be recorded in the snapshot. That means, any message that is sent by a process before recording its snapshot must be recorded in the global snapshot, that is has to be following this condition C1, and any message that is sent by a process after recording a snapshot must not be recorded in the global snapshot, that is it has to follow the condition C2. So, therefore, the condition 2 says that how to determine the instant when a process takes its snapshot. So, a process Pj must record its snapshot before processing a message Mij that was sent by a process I after recording a snapshot. See, these two issues required to be resolved. So, let us see through an example of a money transfer, that is an online banking system. Let us see that you have two sites S1 and S2, and these sites maintains the bank account A and B respectively. So, it maintains the bank account A and this maintains bank account B. Now, site A site refers to a process in this example. So, there is a communication channel from site S1 to S2, and this communication channel is called C12 and C21 respectively. Now, consider the following sequence of action, which is also illustrated in the next slide figure. At time t0, initially the amount 600, A was having a 600 and account B was having 200, and these channel values were 0 initially at time t0. Now, when the time is increased to t1, S1 initiates a transfer of $50 from account A to account B. So, when the time is increased, so account A will be now debited $50, so it will become 550, and since this particular money is debited, it must be in the channel if it is not delivered. So, that will be in the channel, and therefore, it will be debited from account A, and account B is not altered, and that $50 will appear in that channel state. At time t2, S2 initiates a transfer of $80 from account B simultaneously to A. So, it is now sending $80. So, his account will be debited by $80 and it will become from 200 to it will become 120, and there it was 550 and $50 was in the transit. Now, at time t3, S1 receives the message for $80 credit. So, it will be now adding up the $80 and update the account as 630, that is what is shown over here, whereas the account for B is 120, and you can see that C21 is equal to 0 and C12 is equal to $50. At time t4, site 2 receives this 50 credit, and thereby these particular values in the channel becomes 0 and this will become 170. So, A will be having 630. So, this is the correct way of snapshot, and that is what is being explained through this particular figure. Now, suppose if you are recording this global state through the algorithm, and what you find is that record A1 is recorded at time t0 to show the amount as $600 and local state of B and channel is C1 and C2 is recorded to show all these respectively. So, the recorded state shows 850 in the system. So, $50 will appear extra, and this particular region is due to the inconsistent global state recorded. Therefore, this example we will illustrate in the next slide shows that the recording a consistent global snapshot is not a trivial task. So, recording is to be coordinated through an algorithm. So, recording activities of individual computer must be coordinated properly. So, to do this algorithm, let us understand some of the models of communication. So, we will use the FIFO model, where each channel will act as first in first out message queue, and the message ordering is also preserved by this particular channel. So, there is another model of communication called non-FIFO channel, non-FIFO model, where the channel acts like the set in which the sender adds the messages and receiver removes the messages in any random order. So, we are not following this model at this moment. For the sake of simplicity, we are using this FIFO model. Now, the system also supports causal delivery of the message, which satisfies the following property, that if there are two messages, that is, this is I, this is Mij is being sent, this is another Mkj is being sent. So, this process is J, this is I, and so on. So, if the send of Mij is happened before send of Mkj, then the receive in the same process J should happen before the receive of Mkj. So, this ordering is called causal delivery. So, now let us go ahead with the snapshot recording algorithm with the model called FIFO channel model. So, this particular algorithm is given by a famous persons which is implemented in a cloud and distributed system. So, that is called Chandy-Lamport's algorithm. Chandy-Lamport algorithm uses the control messages, which is called the marker, whose role in the FIFO system is to separate the messages in the channel. So, after the state has recorded a snapshot, it sends the marker along out the outgoing channels before sending out more messages. So, marker separates the message in the channel into those included in the snapshot from those not to be recorded in the snapshot. So, the algorithm is initiated by any process executing the marker sending rule, by which it records its local state and sends the marker on each outgoing channel. So, take this particular example. If let us say this is the process who is sending the marker sending rule, it will first record its local state, and then it will send the marker on all the outgoing channels. This is the called marker sending rule. So, the process which executes the marker receiving rule on receiving this particular marker message M, when it is received, when a process receives the marker sending rule M, if the process has not recorded its local state, it records the state of the channel on which the marker is received as empty and executes the marker sending rule to record its local state. So, the algorithm terminates. So, again I am repeating. So, on receiving this marker message, which is special, if the process is not recorded its local state, it will record the state of the channel on which the marker is received as empty and executes the marker sending rule to record its local state. So, this is important to understand. There are two rules in the Chandy-Lamport's algorithm. One is marker sending rule, the other is marker receiving rule. We will explain in more detail about with the example. So, algorithm terminates after each process has received a marker on all of its incoming channels. So, all the local snapshot get disseminated to all other processes, and all the processes disseminate the global state. So, let us see these two rules in the Chandy-Lamport's algorithm. Marker sending rule for a process I says that process I records its state, and for each outgoing channel C on which the marker has not been sent, I sends the marker along C before it sends further messages. So, this is called marker sending rule. Marker receiving rule, that is when a process J receives the marker along the channel C, if the J has not recorded its state, then it will record the state of a channel as empty and follows the marker sending rule. That means now it will initiate this rule. If J has recorded its state, then it will record the state of the channel as the set of messages received along C after J's state was recorded and before J received the marker along C. So, these are two simple rules, and let us take this by an example. So, there are two examples. Let us trace the first example, which is shown by the red one. So, the same running example we have taken for the bank account site S1 and S2, and their initial values are 600 and 200. So, at this point the algorithm will be initiated. So, marker sending rule will be applied over here. So, state, so site A, since it has not recorded, so it will record its state and send this marker on the all the outgoing channel, that is to B, which is shown as the red. So, when it records its state, so its state will become like this, that is 200, 50 and 0. So, it will record its state as the value of A is 550 and B is 200 and the state of this particular channel C A B, yes, C12 is equal to 50 and C21 is equal to 0. So, this will be the marker sending rule will be applied. Now, once the marker is received by S2, marker receiving rule, when marker will receive this particular condition, now what it will do? It will say that if it has recorded its state before that it has not recorded, then in that case it will record its channel state as 0. So, it will record its state of a channel C21 as 0 and then it will apply the marker sending rule. So, marker sending rule will say that it will then record its state. So, when you say that it will record its state, that means it will record state as 170 and 630 and so on. So, just see that this happens. So, let us go ahead by looking up here in this particular case. So, 550 and B will be 170 and C21 will be 80. So, the amount 800 is conserved in this particular snapshot algorithm. Let us see the same algorithm running on another example which is shown over here. So, if A is the site 1, will now run the marker sending rule. Marker sending rule will record its state, that is 600. Now, when the marker will be received by S2 and since S2 has not yet recorded anything, then it will record its state, that is 120 and the channel state of 12 will become 0. But the channel state of 21 will become 80 in this case. So, what we have seen is the properties of the recorded global state in both these possible runs of the algorithm. the recorded global state never occurred in the execution. This happens because the process can change its state asynchronously before markers are sent and received by other sites, but the system could have passed through the recorded global state in some equivalent executions. So, the recorded global state is valid in an equivalent execution if some stable properties holds that in the system before a snapshot algorithm begins, it holds the recorded snapshot. Therefore, the recorded global snapshot is useful in detecting the stable conditions. So, let us conclude this lecture. So, recording the global state in a distributed system is an important paradigm in the design of various applications built around the distributed system concepts, and the design of efficient method for recording the global state is a very important issue. In this particular lecture, we have shown the algorithm working on two different examples. So, this lecture discussed the formal definition of a global state in a distributed system and issues related to that global state capture, and then we have discussed the Chandy-Lamport algorithm to record the global state of a distributed system. Thank you.